So today, what are we got in store? We have got, we're mostly looking at the j-Fet input stage of the RF receiver. There's two things that are very difficult about this, and we'll talk about those things. But first I want to talk you through some theory, kind of get you up to speed on maybe why I did some of the things on the j-Fet stage that I did. It's not to say it's perfect, it's not perfect, as we'll see. And you know, I'd like some advice. I'm not an RF guy, I don't design input stages for a living, you know, not RF stages anyway. So, you know, I've still got things to learn. So we'll start out with a little theory. We'll go back over some theory on switch mode power supplies, because that'll come into it later tonight too. Hint, hint, hint. I hope you're getting the hint. So anyway, yeah. Is there anything else? Nope. I think that's it. So let's move on to the next thing, which is, let's move on to the whiteboard. Alright, first thing I want to do is kind of look at the j-Fet stage. We've got 5-volt USB coming in. There's a terminal block jumper there, so that's what this is. And then I call this my 5-volt and my 9-volt rail, and this is my 5-volt USB. I wasn't very clear on that in the future, or in the videos where I'm actually looking at the scope traces, which I've already shot. So I'll put in notes on there, like, you know, we were looking at 5-volt USB, or you're looking at 5-volt, 9-volt, you know, and that sort of thing, so that you get a frame of reference of what we're looking at. And so that's what the blue pieces are, also WWVB. So those are the three nodes we'll be looking at when we're doing this. So let's see. This is the j-Fet stage we have to work with, right? And this is what I originally designed. I thought it was kind of a good thing. I'm not going to go into details on how I designed it, but this is kind of what I came up with. And just for your frame of reference, also the purple is the dev board that I designed. So when you're looking up here, the purple's the dev board, the black is the dev board with the microcontroller on it. On my board, which is purple, on my schematics, I hope you can make that out. I'm not quite sure you can, but on my board, then I have this filtering of the 5 volts, I have my j-Fet amplifier, and then right here is my antenna. So this is going to be my antenna. And so this is the inductor that the ferrite core rod antenna, I think is what they call them, and it resonates with the 6800 puff capacitor you see there. And so these two things resonate, and they're supposed to pick up the 60 kilohertz over the air, and we've seen that in the past. It does do it, okay? So we know that this circuit is generally working. Couple other things to note. This thing's an amplifier. It's also an inverting amplifier. So whatever's on the input here, this is a short at 60 kilohertz, so it should also go through here. And then on the output, it should be inverted but be much larger. Okay? Now, I was looking at this the other day, and it works for the most part, but there were a couple of minor tweaks that I decided to do just to try and improve the performance of it a little bit. There's a reason I did this resistor divider here, but what I was finding was that a little bit of noise would get on here, and it would actually couple in here and then be amplified on the output, which is not what we want, because anything that's 60 kilohertz there will actually go in to the output stage. So what I've done here is I've simply removed this resistor and I've removed this resistor. Well, Jerome, why can't we do that? Well, because, well, really, you can't right now. This node will now float, okay? And we don't want it to float. So what I've also done is I've removed this capacitor here. And this capacitor I replaced with a little resistor. And I won't explain why right now. Actually, yeah. So I replaced it with a resistor. And so now at DC, this is held at 0 volts through this resistor because this is high impedance. There's no current going through that direction. Because think of the diode here. This is actually a diode, not an arrow. This is a diode. Okay. And so when there's current flowing here, this voltage will go above 0. Okay. So we have the current from the 5 volts flowing through here. And then now this is being held at 0. Well, that's what you want for a j-Fet, okay? MOSFETs are different, BJTs are different, so, you know, but this is what we want for a j-Fet, okay? And so I added this, it's actually a 100 ohm low resistor. And I added it because I was, as you'll see in the videos, there's some weird modulation stuff going on, which I don't know what it is exactly, so hopefully you guys can help me with that a little bit. Anyway, so this anyway, it's all, this is kind of the setup we ended up with, okay? And it works reasonably well, okay? Now I did do a couple other things up here to change the impedance of all this, or to filter my power supply rail a little bit more, okay? I wanted it to be really, really stiff. And we'll get into why here in a minute. But what I did was I didn't actually change these. I'm just moving these. Actually, and now this is 1K. And I added another resistor here, which is also 1K. Now, because of this resistance drop here, I've actually had to adjust this to be 3.9K, or 4K, but thereabouts. I made this 4.7 microfarad, and then I added another 4.7 microfarad here, and then I also have 100 microfarad here. Okay, so I just moved that 100 microfarad right there. Okay, so that's pretty much how it goes. The other circuit that I want to make sure you guys see is a buck regulator, okay? If you've seen this, maybe skip forward a little bit. I mean, if you know what a buck regulator does in discontinuous mode, okay? So again, the purple is my board. The black is the microcontroller board. The blue voltages are voltage we'll look at on the scope. But I just want to kind of give you an idea what this waveform is here, okay? And so what happens is there's a control loop that watches the voltage at 3.3 volts, and it decides how often this switch should be on or off. When this switch is on, current comes this direction and provides power to the load and charges the cap, okay? That current stores energy in the magnetics of the inductor, okay? And then when that switch opens, then that current can't stop flowing. Inductors keep a constant current through them, okay? They can't change current instantaneously. They can change voltages instantaneously, like you see here, but they can't change currents. So when that current through the inductor gets high enough, then the switch opens, and then the current starts going down, okay? But the current then goes through the diode when the switch opens. The switch opens, so the switch is closed, current goes through the switch. Switch is open, current goes through the diode. Okay, and they're both providing current and power to the circuit here. All right. Now, in discontinuous mode, there comes a point where there's no longer current going through the inductor. When the current stops going through the inductor, you end up with the same voltage here as you do on this side of the inductor, assuming the switch is still open, okay? And so what happens is you end up with this waveform where it's been 3.3 volts because everything's been charging, you know, let's assume that it's been working properly. It's 3.3 volts. Switch closes, and now this voltage is 5 volts because you shorted these two nodes together, right? And then so it's 5 volts, and then this voltage here comes up high enough that the control loop says, oh, I need to open the switch. And so it opens the switch. When that switch opens, then this voltage here becomes about 0.5 because you're forward biasing this diode. Okay? Or negative 0.5, sorry. And so that negative 0.5, that current continues to flow until there's no more energy in the inductor to keep sending current. When the current goes to 0, there's no more energy left in the magnetics, okay? And so, but maybe you've still got enough charge in your capacitor to let the capacitor continue to provide energy to your load. And in low power applications, that happens quite a bit, okay? So in this discontinuous mode, you have your inductor current in green, you have your switch current in blue, and it turns off, ramps up, turns off, and then you have your diode current. Turns on, and then ramps down, then turns on and ramps down. And so what that does is here it ends up doing 3.3 volts, and then when the switch closes, now it's 5, and when the switch opens, now it's negative 0.5, and then the current stops flowing, and then it actually gradually goes back up to 3.3 volts. Okay, so that's how a buck mode power supply works in discontinuous mode. Okay, so when the current goes up, okay, you're going to see this frequency get smaller and smaller because you're transferring the energy from the 5 volts to here, and you need more switches to do it because the energy is stored here. And you only have a limited amount of energy that you can store in this inductor. Okay? And so as that frequency starts going up and up and up, well, you'll see what happens. Okay? And then as the load goes down, this frequency gets lower and lower. So what usually happens in something like this is you kind of get a linear ramp up. So this is your load. Your load. And then this is your operating frequency. Okay? As your load goes up, your frequency also goes up. And a lot of times what happens, and I don't know if this is the case on this one or not, but your frequency actually flatlines. Because now you're storing enough energy in the inductor, and then you can do modulated duty cycles to actually regulate it. So anyway, there's a lot of stuff going on there, but the whole point is that I wanted you guys to see this voltage switching, okay, and be able to actually understand it when you see it when it comes onto the oscilloscope here in a little bit, okay? It's a big part of what's going on.
Here's the board we're working with today. You can see it's fully populated. I've got that 3.9K resistor there. I think that's 3.9K. I had to change that so that it would operate down at a real low voltage, because if it's 5 volts, then you have that 1K and then a cap, then another 1K and a cap. Well, then you get to the point where your j-Fet actually is in cutoff mode. Why is this yellow? I don't know. Zoom out a little bit, maybe it'll be less yellow. Anyway, it's fully populated. It's got stage 1, 2, and 3 like we had before. Voltage reference, a single point ground for the j-Fet to have a quiet j-Fet. So what we're going to do today is we're going to turn off all these other things, okay, and we're actually going to drive this transistor on, but in doing all those things, we're going to make sure that we're not actually doing anything else on the board. So what I've done is I've desoldered the coupling cap to the second stage so that there's no power actually getting in. Okay? And we also, the 5 volts is the only thing powering the j-Fet. We're actually going to use a 9-volt battery on it, just so we can see what it looks like in a real quiet environment. Okay? Alright, so here's our setup. We have our antenna, our ferrite rod antenna, and we have a 9-volt battery powering the circuit, the 5 volts, and it's just going into this j-Fet stage right there, and there's a capacitor and creating some resonance there at 60 kilohertz, and so it's exactly what we want. Using the 9-volt battery, we have a real quiet solution. So from a power rail standpoint, so let's see what we get on the scope. Well, there it is. We have the WWVB receiver. I'm connected up just as I explained earlier. I am holding the 5 volts connection to that MOSFET that's actually keeping the j-Fet turned on. I had to bypass that somehow, and so I'm just holding it on. But you can see it's pretty clean. There's obviously a difference between the two, but you know, there it is. So we should be able to receive this signal and see that it's synced and stuff, and sync up to it. See that the measurements are doing what we want it to do. Now it is somewhat peaky. Here, let me turn off, if I can. Yeah, let me turn off the main light that I got going on in here. That didn't really seem to help anything. Sometimes it does, sometimes it doesn't. It's kind of variable. Anyway, like I said, you can see that we're receiving the signal, and it's really good signal. Signal to noise is decent, you know, good enough for a digital receiver to chop that up and receive it properly. So, yeah. Okay, so here's some interestingness about this that I've been discovering, is that, you know, WWVB, they just modulate by sending out loud signal and sending out soft signal. It's very constant. I'm seeing a lot of this here. Let's do a single shot. I'm seeing a lot of this, like a lot of this, like, see how it's kind of very peaky, kind of sort of thing, and that's a technical term called. So, you know, you kind of see how funky it is, right? I mean, it's not just me. I cannot figure out where this modulation's coming from. I've looked all over the place. So here's the board. I just hooked it up to a little 3.3 volt battery operated boost supply. I guess I can put that in the shot too. It's another board that I designed quite a while back. But it's extremely handy for stuff like this. It's just a little battery power supply. So, and it's connected to this and providing power for my application here. Let's see, what's worth mentioning on this? Everything's powered on. Everything should be working. I no longer have to hold that little wire there to keep this transistor on. The subroutine thing is the microcontroller's taking care of that for me. Okay? Alright, so let's take a look at the scope and see what it's doing. Alright, pan over, and let's go ahead and put it on long time base. Oh, well, we're getting some signal, but what is that? I mean, do you see anything there? Here, let me turn off the light. I mean, can you make out WWVB in that? It's going really fast here. Let me slow it down a little bit. Oh, wrong one. There we go. Can you make out WWVB in that mess? I can't. Look at all the peaking. You know, we were seeing 8 millivolts before, and now we're seeing something like 15 millivolts. Okay. I'm gonna move the antenna around a little bit. Let's see if moving the antenna will help us pick up WWVB. The antenna just came disconnected there. Maybe there? Maybe. Let's turn up the gain on the scope there a little bit. Yeah, maybe. But I tell you what, that's going to be really hard to discern in the what's going on the microcontroller. There's just too much noise there. Maybe somebody can do it, but I'm not going to have much success doing that. Look at how much noise is on that. Holy shnikey. I can't see it. I mean, that is a lot of noise. So my first reaction when I first saw this was that it was probably the power supply. And so I did do some looking. Oh, sorry. I did do some looking to try and see if it was the power supply. And I think there was definitely some noise getting in from the power supply. I've got kind of a crude, well, the boost is kind of a crude sort of thing. And I know there's a switching converter on the development board for the microcontroller I'm using. And so I knew that 5 volts was ringing. Okay, so let's go ahead and look at the 5 volts. So here's the switching on the power supply, and this is raw on the 5 volt line on the power supply. And you can definitely see that there is a big dip there, and you know, low ring up and stuff. What is that? I have my suspicions. I know what it is, but when I saw that, it's like, oh no, power supply is getting into my j-Fet. I don't think that's what it is. Not at this point. That's not the primary driver. Just kind of a spoiler alert for the end, but it's definitely not that. Although there's some interesting things at work here also, but you see this coming down. Well, that's why I put those big RC filters on there, 1K and 4.7 microfarad, and then another 1K and 104.7 microfarad. You know, I really went to town on that thing and just filtered the snot out of it. So here, let's look at some more interesting stuff about this. These are kind of new artifacts. These like sharp pulses up. What was that? Oh, I must be shorting something out unintentionally, so I won't do that. So ignore these little high pulses. I think I know what those high pulses are now that I think about it. What they are is probably the switching power supply that I'm using for the 5 volt rail. And then there's not a lot of decoupling on the development board, and so what I think the falling part is the decoupling on the development board is not that great. I mean, you can see we're seeing like 60 millivolts pulses down. Now on my switching power supply, on my external switching power supply, my boost supply, it's much higher frequency switcher, so it's got a lot more stuff going on. In fact, while I'm thinking about it, let's move this high frequency switcher further away, just so it's not kind of interfering. Okay, and so So, I mean, this is what we call common mode noise. It's noise that's common to the system because it's actually being generated within the copper of the system. And I think that's real, actually. And so let's look at the frequency of this dipping. Oh, it's 27.7 kilohertz. Well, shoot, that's really close to 60. In fact, 3 times 20 or 3 times 30 is 90. So, you know, it's operating at 30 kilohertz, and we've got something going on, and then the first harmonic is going to be at 90 kilohertz. Oh, golly geez, I think we got a problem here. I think I see what's going on there. But before we get going too far, let's just kind of take a good look. Oh, I keep changing the wrong one. Let's kind of take a good look at both of them and see if we can see anything going on. Let's separate these a little bit. Yeah, there's something going on there. Let's put it back in free run, or triggered run rather. I'm going to have to give this some more gain. Well, these adjustments can be kind of tricky. And so here we got something going on. Let's just do a single shot capture of it. Oh, wow. Well, what we can see here is every time this kind of blips down, like something weird with the 60 kilohertz starts happening. You see that? There's a little discontinuity, like right here, there's no one right here. Here, let me move the cursors out of the way, maybe you can see it a little better. Yeah. And then, so it's like zoink. And then if we kind of zoom out a little bit, do it again. Oh wow, look, that one's almost flat right there, and this one's kind of going, and well, there's another pulse and it gets a little bigger. You know, it's almost like this is canceling it out. Now let's think about this for a second. Would that be happening because of power supply noise? I will admit that the j-Fet input stage that I'm using is not the best design in the world to eliminate power supply noise. I was not expecting 40 or 50 millivolts. Excuse me, it's getting late. I wasn't expecting 40 or 50 millivolts of power supply noise. I just don't think the power supply is what's doing this. And I can tell you, I've run an experiment to verify that it isn't the power supply by using the 9-volt battery to power just this section of the circuitry. And I can tell you with certainty that this is not the 9-volt battery. You know what? Instead of telling you, let's just do it. Now what we've got going on here is that I've hooked up the 9-volt battery here to the power the j-Fet stage. So this 9-volt battery is quiet. I mean, I measured it, it's drawing 100 microamps or something like that. It's super quiet. It's DC. It's not drawing hardly anything, okay? Here's the same screen capture we had earlier. I'm just going to do a single shot. Oh, but it won't do it. Let's put it in auto. And you can see how quiet the 9-volt battery is. It's incredibly quiet. it is kind of bouncing around a little bit. Not entirely sure why. But really, it's not doing a whole heck of a lot. But if we do just a single shot, will it stop? Yeah. Oh, you saw it there just for a second. Let's see. Yeah, there. You can still see the switching. So that tells me for sure. You see it there? You see it there? There's one here. There's one here. There's one here. That tells me without question that it's not power supply injected noise. Now there might be some power supply injected noise, but that's not the primary thing that's occurring here. Okay? Well, you know, we saw the switching on the power supply and stuff. You know, let's just on the power rail, let's just look at the power supply itself, the switching node, and see if we can figure, you know, just for sure narrow down that it's a switching node. Okay, so up here when it's high, the switch is on. Okay, that high side switch is on and it's connected to the 5-volt rail. Zoom in some more. Yeah, there we go. The switch is on, 5-volt rail. Okay, and then that 5-volt rail turns off, but that inductor still wants the current to come. So then this 5 volts drops down to minus 0.3 or 0.5, somewhere in that range, until the current in the inductors goes back to 0. Once it goes back to 0, then you have no voltage across the inductor, no current through the inductor, and this voltage is now 3.3 volts. That's how that circuit works, okay? And that's exactly what this switching noise is. If we come back here, you can even see it here. See, every time it switches, there's a little change. You know, what's going on there. And, you know, you can see a little modulation of this circuit in there if you look closely. Not sure it's coming out on the video, but you can see it. I can see it. And it's actually modulating just a little bit. Okay? But it's ringing uncontrollably, and it's very noticeable. And so if we go back to this single shot capture, we can see it more easily, and you can see how it's changing between switch to switch. Let's see, let's just do a single shot. There's a single shot. Okay, so here's a switch and it changes the phase. Here's a switch and it changes the phase again. Here's a switch, changes the phase just a little bit here. Here's another switch, changes the phase. Here's another switch, changes the phase. So what's happened? It's not the power supply. I proved that by powering all this j-Fet with the 9-volt battery. Okay? It's not the power supply. What is it? Pause it here. Just think about it. You might already know what it is. Okay. Well, what is it? What it turns out is that thing's switching at, 25 kilohertz, something like that, 27 kilohertz. And what ends up happening is that this antenna is actually picking up the little bit of radiated emissions that it's sending out, and it happens to be just about on the same order as what I expect to be receiving from WWVB. And I am only 50 miles from WWVB. So this thing isn't going to work here, let alone in Florida. And so I've been struggling with what to do with this project. And that's part of the reason I went AWOL as well, is I just didn't know what to do with this thing. I mean, it doesn't work. But I did come up with a list of ideas to try and make it work. Let's see. I gotta pull out my notes here. One of them is to increase the load, increase the load as much as possible. Well, that kind of defeats the purpose of a low power system, right? I mean, but if we increase the load, that frequency will go up, at least in theory. It doesn't in reality, okay? Because it's in this, like, this switch mode, right? It's not in this constant frequency. Turns out this power supply is a variable frequency power supply, and at low loads, it's very low frequency, and then at higher loads, it gets higher frequency. So if I increase the load, maybe I can get it up above 60 kilohertz. That kind of defeats the purpose of having a low power system, right? I've been thinking about powering this off batteries. I can power it off the USB cable. I've been trying to think of ways to kind of keep it real simple. But, so I can increase the load to get it over the 60 kilohertz that I'm trying to receive. I'm not convinced that that's going to help anything, because the switch frequency itself is very, very high. Now it's repetitive at 20 kilohertz, but the switch itself is very, very high, and it's changing the phase of the modulation. And it's doing it significantly in some instances, right? Let's see. Another thing I thought about was making an op-amp input stage. Well, that would work if it was power supply noise. It won't help at all since it's radiated noise, and I'm picking up this radiated noise. I've thought about doing some shielding on this. That's kind of impractical, though. I want to keep it on the dev board. I want to, I can maybe do some shielding on the circuit board, but still kind of impractical, especially considering the long antenna here and stuff. Just still kind of impractical. I've thought about just battery powering it. Again, I want to battery power it. I want it to be low power, so I want the switching frequency to actually go down, which means that I'm going to have harmonics at 60 kilohertz, right? So, battery powering it is something I want to do, but I don't think it fixes the radiated emissions. I've thought about changing op-amps. Lower power op-amps would be able to do this, but I need the high frequency of the op-amps as well. So with high frequency op-amps, you kind of trade power for your high speed. It's that's the devil in it. I mean, that's just what it is. That's the physics behind it. So, you can't have one without the other. And maybe there's a sweet spot there. Maybe these parts are too high a power, and maybe I can cut the power in half and be in that kind of sweet spot. That's an option. I'm not going to discount that as an option quite yet. But that would just lower the frequency, which means I still have harmonics that will be radiated out. And those harmonics of the switching is what I think is actually changing the phase. I can't prove that, but that's my suspicion. The final thing, I think this is the winner, is to ditch the switcher on the development board. It comes with some drawbacks. I can't use the ultra low power. Well, I can use ultra low power modes, but what I can't use is their energy trace thing to monitor which power mode I'm in and see how much energy I am using, how long my battery life will be. And those things can be worked through. I'm not as concerned about that. So what I think I'm going to do is redesign the board actually, and put a linear dropout, low dropout linear regulator on it. So I think that's the plan, is to redesign it. I'd love to hear better ideas. I'd also really like to know if somebody knows what the modulation is when I'm just on battery power supply? That's a big question still in my mind. What else? Yeah, I think that's it. I think that's all I wanted to cover. I mean, this doesn't work. Without the input stage working, it just doesn't work. So if one of you guys that have done a lot of RF knows anything about why that j-Fet's got some modulation on it with a battery, I'm all ears. I'm interested to know what you think it is. Is it just noise here in the room I'm in? I haven't tried looking at this anywhere else except for here in my lab. Anyway, those are my thoughts. Do you have any thoughts? Give me a big thumbs up, subscribe, and leave your comments and thoughts in the comments, because I'm interested to hear what other people think could be a solution to this. Really, I think the LDO is the right way to go, and just power everything off of probably my 5-volt switcher still, but everything else off the LDO. Kind of get that switching power supply out of the equation. So I've also thought about doing a high frequency power supply as well, but then I can control the shielding and I control a lot of things. But first pass, I think I'll do an LDO. It'll hurt me a little bit in efficiency, but I think that's the right way to go. But I'd love to hear what you have to say. Alright. Peace out. 5,000 G. So, if you've stuck around for the whole video, I tell you what, you're actually going to see me disconnect this guy, alright, and then connect this node to a battery. And we'll see what happens. What I'm really hoping happens is that we're able to go ahead and produce, be able to write all our code and all that stuff before I actually have to spin a board to make this low noise. Hopefully, changing this from a loud voltage source to a quiet voltage source will actually help fix some things. Okay? Well, we've seen the bad news, but here's the good news. Okay? Here I am. I've got my 9-volt battery powering my j-Fet, and I've got a couple of batteries powering my 3-volt rail. And if we pan over and look at the scope, we're getting a pretty nice signal there. So I'll still be able to develop all the software before spinning another board. I'll be able to make sure all the other components on the board are working and stuff. Make sure there's no interference between the input RF stage and everything else. You know, I can't really ask for more, really. There's still a lot of noise on the j-Fet, but I think I'll be able to kind of filter that out. Just doing some averaging and stuff like that. So, you know, I think this is pretty good news. So, big thumbs up. Awesome. See you next time.